So I'm from the Faculty of Engineering, and I used to start my talks by saying that the world of scientists may be divided into three groups. There are the theoreticians that understand everything, but nothing works because they don't do experiments. There are experimentalists that have everything working, but they don't understand why. And there are engineers like me, which is the best combination of the previous two. Nothing works, and we don't understand why. So in respect to what the way you introduced me, in any case, usually good presentation should start with a joke. This was a joke. Should end up with a joke. And if it is a really good presentation, the part between the two jokes should be as short as possible.
I'm the joke.
This was the closing joke. So I will try to speed up my presentation. I work in the field of optics. I work in the field of optics. I'm going to speak today about a field which is called super resolution. Super resolution in the near and the far field. The work I'm going to present is compressed. I'm going to focus on a certain direction related to super resolution because of the time limit. But in any case, what I'm going to speak about was done in collaboration with many people from Israel as well as from abroad. The outline of my talk will be as follows. I will start by giving a short introduction. It works, nice. Giving a short introduction, then I'm going to about what a super resolution basically is. Then I'm going to speak about two types of super resolution. One is called diffractive super resolution. The other one is called geometrical super resolution. And I'm going to show you how one can hear with light. And then if we have time, I'm going to conclude my talk. So let us start with the introduction. What is basically resolution? So resolution is the finest spatial feature that an imaging system can resolve. And this is important to emphasize the fact that it is spatial because our sensors, that can be the human imaging system or it can be a camera, an imaging camera, they can sense information not only in the space domain. But when we want to improve resolution, we talk only about space domain. And there are several limiting factors that eventually determine how spatially resolved our image is. There are basically three factors. The first one is related to diffraction. Diffraction describes, the theory of diffraction describes how light propagates, say, in free space. And what happens there is the smaller the spatial feature is, the larger is the angular span at which electrical radiation propagates, diffracts. And therefore, since the imaging lens has a given dimensions, only a given angular span can be of rays of light can be collected by the imaging lens. And this collecting angle defines the smallest feature that the lens can resolve. This is the limitation of diffraction. All the angles which were in larger angular span than the size of the lens will not be collected by the lens, even if the feature was smaller than what we can collect. So this is diffraction. This criteria was defined by Lord Rayleigh and Abbe. And then after diffracting and passing through the limiting factors of the lens, the information arrives to the detector. Now, the detector takes this analog spatial distribution of energy and samples it. And the sampling reduces the resolution further. And this is called the geometrical limitation. And eventually, after reducing the resolution due to diffraction and then due to the sampling, what we need is that every pixel in our sampling array will have sufficient amount of signal-to-noise ratio such that the quantization procedure, the quantization bits that convert the sampled analog value to a digital representation will be such that this will not further distort our spatial distribution of information. So those are the limitations. And the question is, so just as an example, what I told you before, so light diffracts, the limitation, the spatial smallest separation distance that can be obtained due to the diffraction limitation is basically proportional to the ratio between the wavelength, the optical wavelength, the focal length of the imaging lens, and the diameter of the imaging lens. This is the limitation of diffraction. And then, as I said before, this analog distribution is being sampled by the pixels of the detector that convert the digital distribution, the analog distribution into digital image. This further reduces the resolution. By the way, this reduction of resolution, this geometrical reduction, can by itself be divided into two reasons of reduction in resolution. The first one is related to Nyquist sampling theorem, which means that if I take an analog signal and I want to represent it by a digital representation, by a digitized representation, then the sampling, the distance, the spatial distance between two sampling points, 1 over this distance will determine the maximal spatial frequency in the Fourier domain of the analog distribution that I can eventually recover. This is the Nyquist sampling theorem. But beside of this, Nyquist was speaking about ideal sampling, but in our case the sampling is not ideal because it is not done by a train of Dirac delta functions. It is done by pixels. Pixels integrate light. They are not delta functions. They collect light in a given area, they average it. This also reduces resolution. All this is the geometrical limitation. And then the third thing that I mentioned before is that we need to have sufficient signal-to-noise ratio such that the quantization bits for each one of those pixels will be sufficient such that the image that was already distorted will not become image like this. Here, we had only 1 bit of quantization. So all those 3 factors reduce the spatial quality, resolution of our image. And the question is whether the situation is hopeless. Well, if it would have been, then I would not have talked about optical super-resolution. So there is a solution. Obviously, the simplest solution is, OK, so we have limitation due to diffraction, so we can change the lens. Have a lens that can collect larger angular span. So we will have better resolution. Or we can take the detector and replace it with a detector of smaller pixels. Then the geometrical distortion will be smaller. Or we can take a detector which is more sensitive and that has more quantization bits. Once again, the image will look much better. This is possible, and this is the simplest way, but this is maybe possible theoretically, but not always possible in practice, because there are different problems in which we cannot increase the volume or the dimensions or the weight of our lens, or we cannot change the detector by another detector. As an example, let's say that you have a vehicle, an unmanned vehicle, which can carry a certain volume and weight, and you cannot change the camera by a larger camera. Let's say you want to solve some vision problems. You don't want to change your eye with some larger lens. So in certain applications, it's not possible to change your optical hardware. And the question is, can you do something without changing this hardware? And this is where super resolution come into its place. And I'm coming back again to my first slide after the outline, where I said that when I speak about resolution, is the smallest spatial distance between features that the imaging system can resolve. Spatial distance, the spatial information. But our imaging system can capture information in various domains. The information that comes has colors, wavelengths. The information that comes can be captured in different time slots. So the time axis is also an important axis. The information of the light can be polarized or non-polarized. So the polarization of the light is another physical parameter that we can play with. And therefore, basically, what is super resolution? Super resolution is a concept in which you combine simple optical hardware that does not increase the volume of your system together with some processing, image processing, in which we do some kind of encoding of the spatial information, the high resolution spatial information available in our object. We do some kind of encoding or conversion of this information into some other domains. What domains? Like polarization, time, wavelength, colors, and so on. Transmitted through the band-limited system that we have without losing this information, and then doing decoding, deconverting back the information into the space domain and recovering the spatially high resolution image. This is super resolution. Now, in order to be able to do this, we need to have some a priori information about the type of problem we are dealing with. Because if I want to take the spatial degrees of freedom, the spatial information available in the object, and convert it into a domain, say like time, I need to know a priori that the type of problem I'm dealing with is the type of problem in which the time axis is available for us. So there is no time variations in the object. The object does not have temporal information, because if there is an object which I want to resolve in space, in high resolution, it is also a very dynamic object that is changing in time. I will not be able to use the time domain to convert this information. And so on regarding the other domains. So I need to have a priori information. And when I have this a priori information, I indeed can use other domains to do this encoding and conversion, and then transmitting through our system the information, and then doing the back conversion. We'll not go into equations. In the diffractive type of super resolution, I want to focus in showing what is called time multiplexing super resolution. Although, as I said, we can use other domains in order to do this conversion of degrees of freedom. And I'm going to show you how to do time multiplexing in several steps. I'm first going to show the basic concept for you to follow me. And then I'm going to show how we can improve this concept to make it more applicable to a more general type of problems. So let us start with the simplest thing. This is an object, and this is an image. Those are lenses, and this is basically a schematic sketch for an optical imaging system. Okay, you don't need to know optics, just trust me that this is a schematic sketch for such a system. What we have here is an aperture. This aperture, which is limited in size, resembles the fact that the lens has a limited size as well, and therefore, due to diffraction that I told you before, we have limited resolution because the angular span that the lens can collect is limited because of this limited size of the lens. Now, object and image. Now, what is the time multiplexing technique I'm talking about? Let me explain it in the following way. So the object has spatial features which are small, sufficiently small, that they cannot pass through the aperture of the lens, because the aperture in the lens is basically the Fourier transform of the object. And since the small features here generate high spatial frequencies, they are blocked by the aperture. So what can we do? If, for instance, we take a grating and put the grating very close to the object, and excuse me?
What is a grating?
Grating. What is a grating? We take a periodic structure, say a periodic structure like this, lines.
Okay.
It's an excellent question because I have an answer and a slide to show you. You know, there are good questions. You ask me, I answer. Excellent. When you ask me, I have a slide and an answer. And then there are, of course, interesting questions. This is when you ask me, and I'm, as a presenter, also very much interested in knowing the answer to the question I was asked. So this is an excellent one. In any case, assuming, so we have here, this is called a grating, a set of lines. Say that one of them is the object I want to image, and the other set is this encoding pattern that is positioned next, attached to the object, okay? Now, my imaging system cannot resolve those small spatial features, cannot, because, as I said, due to diffraction and due to the fact that the imaging lens is limited, the spatial frequencies in the Fourier domain that are generated due to those features are higher than the limitation of the imaging lens. But what happens if I put the encoding grating next to the object? What we have here, I mean, if we look on each one of them separately, they are just two gratings, okay? But when I put the one on top of the other, what do I have? I have the generation of those lines, right? You see those lines? those lines have large spatial period. They are low spatial frequencies. Those lines will be able to be imaged by the imaging lens. This is called the Moire Effect, if you are not familiar with. And by the way, if I take my encoding grating and I change it, you see the period of those lines is also changed. You see it? Right? In any case, by putting this encoding structure next to the object, we down-convert the high spatial frequencies that could not pass through our imaging system. We down-convert them into low band of frequencies that can pass through the system. Excellent. So now we see those lines. We know a priori what the encoding function was. And of course, the encoding function should contain small features as small as the final resolution outcome that we want to obtain in our super resolved system. So we know the grating. We see this. We can, from this, obtain or estimate the original object. But there is a problem. How will we be able to separate between the high spatial frequencies in the object that were down-converted due to this encoding to low spatial frequencies and the low spatial frequencies that originally were in the object? They will be mixed, right? So this is why in this setup, this encoding grating is not a static one, it is moving. So this system, this imaging system, has an encoding grating which is a moving one, a decoding grating which is identical to the encoding one, and it is also moving in the opposite direction because imaging system like this has a magnification of -1, so everything is inverted. And why movement solves the problem that I have mentioned before? Because what happens here is what is called a Doppler something which is similar to a Doppler effect. What is a Doppler effect? Those of you who don't know, if there is a train coming and the train is using the horn, it is coming closer towards you or it is going away from you, you will hear the horn as a different frequency. This is a Doppler effect. Now, because this is a moving grating, what happens is that high spatial frequencies that were down-converted to the low frequency will have large Doppler shift in time. And the originally low frequencies that were not down-converted will not have a Doppler shift. So the higher the frequency is, the higher the Doppler shift is. I don't know what it is, and I don't care, because what will happen due to miraculous optical features, which I will not go into them, by having the same decoding grating as the encoding one, moving with the same frequency, the optics will properly do correction of the Doppler only to the proper frequency. So the high frequencies will be separated from the low frequencies because they have different Doppler, and the decoding grating will correct them properly. It will reconstruct the object in a proper way, such that after transmitting through the system the low spatial frequency, it will multiply the low spatial frequency by the decoding grating, and because of the Doppler, it will properly correct, properly shift in the spectrum the high frequency that were folded to the low. It will properly shift them to the right spectral position, and the low frequencies, which were not downshifted, that don't have a Doppler, will stay in the same place. This happens by itself. The only thing that we need to do is to time integrate. This is why this technique is called time multiplexing. So we just time integrate, collect information. And of course, we move the decoding grating and the encoding grating, and we super resolve without changing the imaging lens. Those are some experimental results. So we have here 3 experiments. We have 3 objects. This is how they look like with a high quality lens. This is how they look like in a low quality lens. So they are blurred. The spatial information that was here disappears. This is garbage. And then we take this bad lens and we apply with this bad lens the super resolution technique I showed you before, and this is what we get. We have the reconstruction of the high resolution reference objects without having the high resolution imaging lens, just by having the moving encoding grating, a synchronized moving decoding grating, and doing the time integration. This is very nice, but it has several limitations. What are the limitations? I'm very glad that you asked me this question. The limitations are that in microscopy, where we have objects which are close to us, we can access the object, we can put the encoding grating next to the object, and we can put the decoding grating next to the detector, We can time integrate, move them both, everything is excellent. But what happens if we are not dealing with microscopy? Say I want to image something which is far away. Say that I'm a camera of a satellite and I want to image something that's moving on the ground. I cannot go there, place a grating, go back to my satellite and take an image. I mean, if I went...
The problem by itself.
I didn't tell you how long I was time integrating. Yes, if I started by saying that when I do time multiplexing, I need to assume that during my time multiplexing period of time, the object is static in time. So in this time, the object should not move, but I did not say how long this time is. If it is 1 nanosecond, it should be okay, right? So I didn't speak about this yet. I will speak about it. But besides the time integration, if I go to the object to put the encoding grating, then I didn't gain anything. So how do we apply the same technique without going to the object? So the next step in the developing of this concept was to project an encoding grating rather than putting it next to the object itself, to project it from a distance. But here you need to be very careful because, as you remember, in order to super resolve, I had the encoding grating to have small spatial features as small as the outcome of my super resolution. And if I have an optics that can project such a small spatial features, then this good optics can also image in the same resolution the object I look at. So there is no point in doing super resolution. And therefore, when I do the projection, I need to do it in such a way that I'm not using the high and the large and the expensive optics that I eventually want to avoid of using. But there are ways of doing it. So for instance, what we did it by interferometry. We took several light sources. What happened is that light sources in far field generate interference gratings. The gratings are generated by themselves. We can project light on the object just by putting several light sources that will interfere on top of the object, generate this interference grating. We collect the light. Instead of doing decoding grating physically, we can do it digitally. So what is a decoding grating? It was moving next to the detector, so we can capture an image and multiply it digitally by the decoding grating, and instead of time multiplexing, just to sum all the images. And this will also give us super resolution, like here, this experiment. So we took a reference object that had a thick line, thick, thin, and so on. This is with a high quality optics. With bad optics, the thin lines are blurred. We cannot see them because of lack of resolution. And then when we apply the projection I told you about, we can resolve those thin lines, and it works. So this is nice. It is an improvement, but still not sufficient improvement. Why? Because projection through interference, as I told you, is possible, but not always simple to do. I want to do it in a simpler way. So the next step was, instead of projecting through interference, instead of projecting the grating, what we did was to use a self-interference effect of spatially coherent light, an effect which is called speckle. What is speckle? If I take a laser beam and I illuminate a surface, you will see a spot of light, right? But if you look closely on this spot of light, you will see that within this spot of light, the spot is not uniform. Within it, you have smaller spots, which are smaller spots of light and spots of darkness. And this is a self-interference of the light with itself that happens due to the fact that the surface is not flat, it has roughness. Okay? Now, those speckles within the spot of light are generated due to the roughness of the surface, but I can also project them. How can I project them? Very simple. I can take a diffuser. You know what a diffuser is? A piece of glass, which is a diffusive glass. When you, like matte glass, and you illuminate through it, the light will be diffused. And when you illuminate through this glass on top of an object, you will have many small spots of light. They are called speckle. Very simple. I just take a diffuser, I take a light source, and I illuminate on the object. I image the reflections with my camera and do the decoding by multiplying every frame in time that I capture with the decoding pattern, which is equivalent to the pattern that I have projected through my diffuser. So here are some experimental results. we took a resolution target, which is called the rosette. Rosette is a target that looks like a sun with rays. So we have rays. The closer they are to the sun, they are more spatially dense. The far away they are less dense. Now, this is a resolution target that tests the capability of resolving in an imaging system. 5? 25. Okay, I will speed up. In any case, what we saw is that when we have this low-quality imaging system, it is either garbage, you don't see anything, or you see some. It is either garbage or you see something, but the high frequencies are blurred. And after super resolving, we see that the high spatial frequencies are well reconstructed. Still, this technique is not, and of course, it can be done also for microscopy. Here you have cells, reference images, blurred images, super resolved images that resemble the original one experiment, another experiment. So we use these low quality optics and we resolve those high quality images. There is still one disadvantage, and disadvantage is that we need to be active, we need to illuminate, right? We need to project. Sometimes it is possible, not always. In military applications, you want to be passive. And the next step was to use given a priori information about our environment in order to be passive. If we have a target moving on top of a background, let's assume that the background is our encoding pattern. We don't need to project it. The target is moving, so there is relative movement between the target and the encoding background, like we had before, but this time we don't project anything. Of course, we need to know a priori, in high resolution, the background in order to use it to decode the information. Like before, we had encoding and decoding, we had to know how to decode. So we take a high quality camera, we map the reference, we put it in the memory of our computer, and now we take a low quality imaging sensor or optics, and we observe. Whenever there is a moving target coming into our field of view, we will use, it will be captured in low resolution, we will use the a priori known high resolution background in order to decode the images exactly in the same technique we did before. You see here some simulations of airplane moving in front of a background. This is how the low resolution images look like. This is how it looks, the reference airplane looks in high resolution. This is how it is blurred due to the low quality optic. This is the reconstruction where you can see it is much better, resembles much better the original airplane. And then some experiments. So there was a student driving a car in front of this background. This is the low resolution images we captured. And from this, we could able to reconstruct this where we see the high quality outline of the car. It was a Jeep. The next step, there is still one disadvantage in this technique, and the disadvantage is that we still need to know the encoding pattern in high resolution in an a priori way. So it's possible, but it is some complication. So the next step, the last step, to make it more practical, this technique, was to use the following concept. Say that we have many particles. And those particles, the only thing I know about them, they are small. The only thing I know about them is they are sparse. And they are floating in proximity to the object that I'm looking at. This is, by the way, a problem from a microscopy. So I put on top of my object a droplet with water. Within it, many nanoparticles. They are floating next to the object due to their Brownian movement. And while they are floating there, I see low-resolution images. The particles are blurred, but because they are sparse, the blurring spots do not coincide. So for every image that I capture, I allocate the center of each blurring spot, and I extract the high-resolution decoding pattern from the low-resolution images, because I find the centers, and the centers is where the particles were. I can construct the decoding pattern without knowing anything. Everything is passive. We use this in microscopy and constructed what we call a nanoscopy. We were able to see sub-wavelength, very small nanometric features in a regular optical microscope just by putting a droplet of water with nanoparticles floating there. But of course, it can be used also for remote sensing, because if you have rain, for instance, it is a very similar problem, because droplets of rain are once again very small droplets, which are sparse enough. We capture a set of low-resolution image, and we can super resolve, like you can see here, This is a reference target captured in high resolution. This is how it looks like from a low resolution sensor. And after super resolving, all those spatial frequencies that were blurred are recovered by the technique I explained you. Okay, very shortly about geometrical resolution. I will go directly into this. I explained that the geometrical resolution is basically reduced because of the fact that the pixels we have a certain pitch, they have a certain distance, sampling distance, and this sampling distance, according to Nyquist criteria, determines the maximal bandwidth, spatial bandwidth of frequencies that we can reconstruct from our analog distribution of light. The way to overcome this is by doing what is called microscanning, means capture an image, shifted by a subpixel, capture another image, and you increase your spatial sampling density, but it does not solve the fact that the sampling is non-ideal. It's not Dirac delta function because every pixel averages in space. How do you solve this? So we have developed a technique in which we take a random mask and position it in an intermediate image plane. And what this mask does, why basically we have reduction of resolution? Because if we have 5 spots in space in the object and the pixels are 3 times larger and they do average, we have 3 equations, but we have 5 variables, so we have more variables than equations. We add this random mask, which is a priori known to us, and this mask blocks certain transmission. It is a binary mask. It blocks light transmission in certain a priori known spatial positions, and this blocking adds us more equations. When we have more equations, we can invert our matrix that represents this complex of high resolution image, and after doing that we can super resolve. This is the reference resolution target. This is how it looks like due to the reduction in the geometrical resolution. This is the reconstruction we obtained by 3 different random masks. We see that the high spatial frequencies of the reference are indeed reconstructed, although we use this low resolution image. The last thing I'm going to show you, because the time is short and the chairman is getting nervous, is that we can basically listen with light. We can not only improve spatial resolution, but we can use light in order to hear things. Not because we are schizophrenic to hear sounds, but really we can hear with light. How can we do it? So we have developed a technique which is basically includes a camera, a lens, and a laser, that's all. And we illuminate a certain field of view. And we look on this field of view with a camera, this camera, okay? Now what happens, I told you before about the speckle. Those are random patterns being reflected from the surface of the object that we look at. Those random spots are also will randomly move if the object is moving. Randomly change, sorry, if the object is moving. We do something with the optics we have such that this random distribution is now not randomly changing, but changing according to a certain set of rules. We track how they change and compare it to how they should change. And from this information, we know in very high resolution how the surface is moving. The surface can be anything. If it is this surface, we can hear what was said. If it is this surface, we can extract the blood pressure and the beating of the heart. If it is, every surface has a different information. And we use this technique to listen to people, to tap to cellular phones, to extract biomedical parameters like blood pressure, heart beating, glucose concentration, alcohol concentration in blood, intraocular pressure in the eye, and other very important biomedical parameters. Just as an example, this is me. And by the way, the distance is not important here. So we can listen from hundreds of meters.
You can listen to people talking in the room by the vibration of the window.
This was done in the 70s. But that, yes, it is taken from the James Bond movie. Come on, even I saw it. Actually, this was the motivation. It was the motivation for us to do this, because that technique from the 70s had 4 major disadvantages. The first one was that it used an interferometer, which is a not portable enough device. We don't have interferometer. Secondly, you had to be more or less in the same height as the window, otherwise the light was not back reflected to you. We do not have this. Third thing is that if you had several people talking simultaneously, or you have a speaker and a noise, it was mixed. You could not separate them. In our case, we work on an image, and since each one of you is a different pixel, I hear you separately. If your voices I hear separately. I can hear millions of voices simultaneously and separate them, or a noise and a signal. And the fourth thing is that that technique that you have mentioned was not working with the skin. So you had the person to walk on a street and carry a window in front of his face. Not always practical. But we can do it in any circumstances, and it works. In this case, and I'm really done. In this case, it's me. Students sent me to a distance of about 80, 90 meters. They told me, OK, Zeev, in the walkie-talkie, Zeev, turn on your heart. And I turned my heart. And then they illuminated my chest. And they hear the beating of my heart, as you can see here, from like 80, 90 meters. This is the beating of my heart. And I was in a construction site, very noisy site. You do not hear it. You hear the beating of my heart. Can you hear the beating of my heart now? You cannot. This was from 80 meters, 90 meters. And then we tapped to cellular phones like here. We could hear what was said on the other side of the line. In this case, it was 1, 2, 3, 4, 5, 6, and so on. Come on. We could hear what people were saying by examining the reflection from their neck and so on. The time is short, I will not go into this. Just tell you that we use this not only to listen or to tap to cellular phones, but to extract very vital and important biomedical parameters, such as heart beatings. This is the beating of heart. So you see how we measure it without a contact. Blood pulse pressure. This is a clinical trials in which we compare our measurement with a reference sleeve device. You can see how the two curves coincide. We could estimate a concentration of glucose. This is a reference measurement by a glucometer and our measurement. We could measure intraocular pressure. The pressure, this is a very important parameter to people having glaucoma. We could measure it, once again, from a distance in a non-invasive way. And I'm done. Conclusion. Whoa. Okay. So I spoke with you about how you can use various techniques involving optical hardware and image processing to see better, but also to use light to sense various medical as well as non-medical information, like to listen to people, to tap to cellular phones, and so on. Thank you.